Hello everyone, welcome to our discussion of section 8.3 where we will be talking about the integral and the comparison tests for testing whether a series converge or not. Now before we begin, a couple of things first. On the screen, as you can see, in this section 8.3 we will only talk about tests that are applicable to series that have positive terms only. Now, in the next section, 8.4, we will talk about tests that apply to series that have positive and negative terms. But in this section, we're only focusing on testing series that have positive terms. Okay. Once again, as I mentioned in section 8.2, it's worth reminding everyone again that we learn about series and whether they converge or not because series are often used to model solutions of very complicated equations. So with that's why when we talk about the series converging, we're talking about the series converging to a solution to some complicated equation, or at least that's one of the applications of it. There are many other advanced applications of this series in computer science which I'm not familiar with, but those are at advanced level. If Math 182 or Calculus 2 is the last class you're taking, you probably will not encounter those applications, but if you are taking senior level or graduate level math courses later, I'm sure you will encounter such applications. But I thought to say a few words about that because the question does come up, okay, what does it matter that a series converges or not? So this is why. So we use this for solving complicated equations. And I just included a few words here on the first page, which I will post on Canvas for those of you who are interested. So back to integral and comparison tests. Again, these two tests apply to series that have positive terms only. And so often we have, it's difficult to compute the partial sums. So there are tests that we could do to replace that and decide whether series converge or diverge. So the integral test, that being one of the two tests discussed here, or one of the two or three actually, the integral test, suppose f is a continuous positive decreasing function on this interval. This is a loaded sentence because each of these conditions, if they're not satisfied, we cannot use the integral test, okay, on this interval. So it must be that the function is continuous. It must be that the function is positive, and it must be that the function is a decreasing function. Okay, on this interval. So you could have a function that has erratic behavior in other regions of the plane, and it doesn't matter. As long as it's positive and decreasing over this interval is what we care about. Notice this interval is the same interval where a series is usually investigated or drawn out, right? We take n from 1 to infinity. So that's why we care about these conditions over this interval and not other intervals. Okay? So let a sequence represent a function at n, or vice versa. Then if we replace the n with x, and we integrate from take the improper integral from 1 to infinity of that function, where the n is replaced with the variable x, if this integral converges to some real number, some value, then the integral is convergent, and we can conclude that the series is also convergent. But if we take the integral from 1 to infinity of that function f of x, and we end up with something like negative infinity or positive infinity. That means the integral is divergent, which also means that the series is divergent. Okay, so, and note that it is not necessary to start the series or the integral at n equals 1. So if you have a series that starts at n equals 4, this is just being an example, then you can use the integral test starting from 4 to infinity. Okay, but the point is that this is the interval, the integration limits are the same as the ones set by the series. Whether it's 1, starting at 1, 2, 3, or 4, it doesn't matter. And the other important note here is that it is not necessary that f be always decreasing over its entire domain, that is. That's what I was saying a little bit earlier, that as long as the function is continuous, positive, and decreasing over this interval, which is the same interval where we're evaluating a series, that's all we care about. If the function has other behavior, say increasing outside of that interval, it's okay. It's totally okay. And that's what this note is all about. It is not necessary that f be always decreasing, but that f be ultimately decreasing. And here at the bottom, a significant note here that if sometimes, this is not always the case, but sometimes a first derivative of the function can be used to establish this. Okay, so once we replace n with x, we have f of x function. If you take the derivative of that, it'll tell us, right? We learned in Calculus 1, using the first derivative test, that if the derivative is less than 0, then the function is decreasing over the same interval. Okay, but that goes back to the first derivative test. So keeping in mind those three conditions for the integral test, that the function should be continuous, it should be positive, and it should be decreasing, let's approach some examples here. So here we want to use the integral test to determine whether the series is convergent or divergent. So first, let's replace n with x. So we'll get a function 1 over x to the 5, right? So we can say that the function 1 over, the function f of x equals 1 over x to the 5th power is continuous. Of course, at 0, it does not exist, right, this function. But we don't care, because look where the integral will start. It will start at 1 going to infinity. So over, this function is continuous, positive, and decreasing. It meets all those three conditions for us to be able to apply the integral test on this interval, 1 comma infinity, which is 1, which matches that n going from 1 to infinity. Okay, so the integral test applies or is applicable. Okay, so based on that, let's take the integral from 1 to infinity of 1 over x to the 5th power dx. And of course, this is an improper integral. We've learned how to handle these. So we'll replace the infinity with t variable. So 1 to t of, and let me rewrite this so it's easier to integrate, like that. So after that, we can just calculate the integral, and this would be negative 1/4 x to negative 4 power from 1 to t, right? So then this would be, I guess, so maybe I can fit it right here. So this would be equal to limit as t goes to infinity of negative, so let's just substitute for x with t, and then I guess I'll rewrite this as minus 1/4 t to positive 4 power, right? Putting it in the denominator, and minus, and then 1/4, right? Because substituting for x with 1, this is just minus 1/4. Okay, so then after that, so this will be positive 1/4, and if we apply the limit to this t, we get minus 1/infinity, which is 0. So we'll end up with 0 minus minus is plus 1/4, and so we get 1/4 for this improper integral. So of course, the integral did converge, right? So this so the result is that this improper integral is convergent. So the series that we had, let me move this up a little bit, 1/n to the 5th power, is also convergent. Okay. I guess I can box that too, like that. Let's do another example. This time we have the infinite series 1 to infinity of 1 over square root of n plus 4. Okay, so let's see if we can determine if this function is continuous, decreasing, and positive over this interval, 1 to infinity. Okay, so the function f of x equaling, so let's see, so this would be substituting for n with x plus 4 to minus 1/2 power is continuous. So it's continuous. And because over this interval, this denominator is never 0, right? Which would be the only, or never 0 or negative. So we don't have to worry about any of those cases that would make this function undefined or discontinuous. So we know it's going to be continuous over this interval. And we know this denominator is always going to be positive. The numerator is positive. So this is also going to be positive. And also because we're dividing 1 by some increasing quantity, so this is a decreasing function. And decreasing on that interval. This is important to make a note of, on 1 comma infinity. Okay, so we can apply all three conditions for whether or not we can apply the integral test are satisfied. And notice that sometimes it's so easy to establish whether or not all three conditions are true. Okay, so we really didn't have to do much to establish all three. Okay, so then applying the test, we have 1 to infinity of that. So we have x plus 4 to minus 1/2 power dx. And this is an improper integral, so we have to treat it accordingly. 1 to t dx. And of course, this is taking the integral of this, add 1 to this, we get positive 1/2, divide by the new power, which would make this 2 times that. So then we have limit as t goes to infinity of 2 times x plus 4 to 1/2 power, which should be evaluated from 1 to t. Okay. All right, so let's apply the limits of the integration to this before we apply we decide that t should go to infinity. So this would be limit as t goes to infinity. So this would be 2 times t plus 4 to 1/2 power minus, substituting this with 1, we get 5 to, so this would be square root of 2 times square root of 5. Like that. Now if we apply the limit to this, of course, this is going to be infinity. Infinity, something taken away, so subtracting 2 square root of 5 from infinity, it's still infinity. So we have minus like that, or infinity. So the integral diverges. So the integral leads to this, not some real number. Therefore, so I should add here, thus the series diverges or divergent. Series square root of n plus 4 diverges. Okay, like that. I hope this is making sense. We just have to be careful about these 3 conditions before applying the integral test, making sure that the function is compliant with these. Okay, so next we get to, before we talk about the comparison test, which is coming up next, we have to talk about the p-series, because p-series is used in conjunction with the comparison test. These two, the p-series and the comparison test, are used in conjunction with each other. So let's first talk about what is a p-series. So the p-series is that, exactly what you see on the screen here, 1 over n to some power, right? N is incremented by the index from 1 to infinity to some power, is convergent if p, this power, is greater than 1. So if it's 2, 3, 4, anything greater than 1, then the p-series is convergent. If p is equal to 1, in other words, if you have a series from 1 to infinity of 1 over n, that is divergent. That means p is equal to 1, or if p is less than 1, then the series is divergent. Okay, so the only condition or the only case where the p-series is convergent if its P, this P is larger than 1. Okay. And this is just a reiteration of what I said here because it's so important and it does come up often. That case where we have P equals 1, which means that the P series is divergent. So we will use the P series in conjunction with the comparison test. And you'll see in a few seconds, you'll see why. So in the comparison test, suppose that you have some series A sub n, and this is the series that is being tested. And series B of n, this is the series that you pick. You select this series. This is the series that is being tested using the comparison test. But being just looking at the name comparison, what do you compare it to? You compare it with the series that you pick. You're selecting the series B sub n, and this is what you're testing. So, suppose these are the two series, one which is given and you're testing, one which is what you pick, with positive terms, of course, they should have positive terms, where the one that you're being, the series that you're testing, where this is being tested, and I'm just adding that because in the book there's a little bit of confusion which is which. So this is the series that is being tested, and series of sigma Bn is the series that is an appropriate selection by you, which is usually some form of the P series, or a geometric series. The point is, when we say this is what you have to pick, you're picking a series that is familiar to you. That is either a P series or a geometric series, because you know when P series and geometric series diverge or converge. That's why we're saying you're picking a series that is appropriate selection by you. So this should be an appropriate selection. Whether or not it's appropriate, it depends on what this is. It depends on what series we're testing. Okay, you'll see examples of it, so you know exactly how this method unfolds. So, given those two series, one that is being tested and one that you've picked, either a P series or a geometric series, then if the series that you picked, the power series or the geometric series that you picked, is convergent and it's greater than the series that you're testing for all values of n, then the series that you're testing is also convergent. So this small box is pretty compact with information. Please make sure that you slow down. As you read this, please make sure that you slow down and think about what it's saying. That the series that we've picked, it could be either a geometric series or a power series, because we know when these two kinds of series converge or diverge. If that series is convergent and it happens to be larger than the series we're testing for all values of n, then the series that we're testing is also convergent. Now, if the series that we've picked, the geometric or the P series that we've picked, is divergent, and the series that we've picked is smaller than the series that we're testing for all values of n, then the series we're testing is also divergent. Now, with respect to each of these, case 1, case 2, I've included a note here, because the comparison test does not apply when the terms of this series being tested, that means this one, sigma an, when the terms of the series being tested are larger than the terms of the convergent series. The reason is because we said that the convergent series should be greater than the series that we are testing. But if the terms in the series that we're testing are larger than that, so this doesn't apply anymore. the series we're testing, the terms should be smaller than the series that is converging. But if the terms are larger, in other words, the opposite of this is true, then the comparison test does not apply. By the same token, for case 2, if the series that we're testing, if the terms in this series are smaller, notice that in case 2, they should be larger. The terms in the series we're testing should be larger than the series we've picked. But this is saying that if the terms in the series that is being tested are smaller, in other words, the opposite of that, then the terms of the divergent series, then this does not apply. So these are cases where this comparison test does not apply. This is just one page, but it's packed with information and conditions and the things you should know. So please make sure that if you have to read this page several times in order to fully understand what this is saying, please, it is worth your time. So please take the time to do that. So keeping this in mind, let's apply the comparison test and probably the p-series to some examples. So this is saying use the comparison test to determine whether the series is convergent or divergent. Okay, so we will begin by, so we know that with the comparison test, so this is the series that we're testing is sigma a sub n, right? Let me write that down. So in our case, well, let me write that down here. Sigma a of n is what we have, n over 2n cubed plus 1, right? So we have to determine, using the comparison test, we have to determine what is sigma a n and what is sigma b n, these different two series, okay? So that's the one we're testing. Now this, we have to pick. So to notice that this is smaller than n over 2n cubed, right? Because the denominator, so let me actually write this down. So note that this, so 2n cubed plus 1 is less than n over 2n cubed. This is a really convenient pick. So actually let me write down here that sigma bn would be equal to that. That's what I'm implying here. That let's set this other series that we have to pick as equal to that, n over 2n cubed. So if you compare these two, clearly this is going to be larger quantity, right? Because here the denominator is larger. So we have a smaller quantity here, we have a larger quantity there. So if we simplify this, we will furthermore, and also note that, and also that this quantity is less than, so this is, if we simplify it, before I go to that inequality, and I will clean this up before posting it on Canvas, but if we simplify this, what do we get? We get 1 over 2n squared, right? That's what we get. Now this is for sure less than 1 over n squared. Okay, this is looking like a p-series, right? 1 over n to some power p. So then if we take what we have up here and what we have here, we can write this. Thus, this quantity that we have, that we're testing, is less than 1 over n squared. right? Just compare everything we've done here and here, and you will arrive at this conclusion. So, and then this is a p-series with p equals 2, which is greater than 1. If I bring this slide back, so if p is greater than 1, in our case is 2, then the p-series is convergent. So note that this one, so this series, I'm putting this in a series, is a p-series. With p equaling 2, which is greater than 1. Therefore, the p-series is convergent. I move this up a little bit. Is convergent. So if we look back at that box, in the convergent case, the series that we pick must be greater than the series we're testing. And we've already established that the series, this is simply akin to that. I mean, this is even larger than that we picked after simplifying it to this, and this is less than that. So this p-series for sure is larger than that. So we've satisfied this condition. The series that we have is larger than the series we're testing. In the convergent case, that means that the series we're testing is also convergent. So therefore, and so this is, so this, because of that, then we can say that by the comparison test, right? This satisfies the comparison test right there. And this one and this one, these two actually I should highlight this and this. These two. These two. By comparison test, the series that we were testing is also convergent. Converges. Okay. Like that. So notice how in this example we used p-series in conjunction with the comparison test. So let's do another example. This time we want to test the convergence or divergence of this series. Notice right away that this is starting from 2. Like that. Okay. So first of all, we know that, let's write this down. So we know that the series we have, and well, let me actually start it and establish what the AN is and BN is. So this is our series AN, and series BN, we're going to take that as, let's start with n cubed over n to the 4th, like that. Because this is going to reduce, or this is going to actually simplify, not reduce, but simplify to, so if this is going from 2 to infinity, this should also go from 2 to infinity, and this should also go from 2 to infinity. Let's simplify this. We get 1 over n, right? This is the harmonic series, right? So we know that a harmonic series, part of the harmonic series starting from 2, n equals 2. 1 over 2 plus 1 over 3 plus 1 over 4 and so on and so forth. Harmonic series diverges. So we already know, this is why when I say that the series that you pick should be a series that you know whether it diverges or converges already. This is the one you're testing, but this one should be the one that you know how it's going to behave. So we know this harmonic series is going to, which is also a P series with P equals 1, by the way, right? It's also, we can call it P series with P equals 1, either way. Okay, so given that, then we know that n cubed, the series that we're testing, is larger than that, 1 over n. Okay, so that's that. And therefore, and we know that if I put this in a series with n starting from 2, we know that this is a P series with P equals 1. Thus, this is divergent. Is divergent. Okay. Now, if we look back at the divergent case, the divergent case of the comparison test, notice that the series that we picked, in order for this to apply, the series that we picked must be smaller than the series we're testing. In this case, we've already established that. Right? So this is clearly, this is going to be this one. It's going to be smaller than this, right? Because let me actually add that here, right here, right before that, before this line, I can add is greater than n cubed over n to the 4th power. Because the numerators are the same, the denominator here is smaller, right? So it makes this fraction bigger than that. So once we know that, and of course 1 over n is just this fraction simplified, so this leads to that, after which we built this case, that this is a P series, it is divergent, and because the P series is smaller than the series we're testing, for the divergent case of the comparison test, we have satisfied all the conditions. Therefore, by comparison test, so by the comparison test, this series also is divergent or diverges. Okay, so that's that. Okay, so next we will look at another type of test. So we looked at the integral test, we looked at the comparison test. Now We are talking about the limit comparison test. Again, this is another test that applies to series with positive terms. So when the comparison test does not apply, and we mentioned when it doesn't, right? At the bottom of the page 4, this is what I'm referring to when I say see page 4 of the lecture notes. That's what I'm referring to these two conditions, when the comparison test does not apply. These are the cases, okay, in relation to when the comparison test applies for the convergent case and when it applies for the divergent case. So these are the cases where the comparison test will fail. We cannot use it. So when that happens, another test we can probably use is the limit comparison test. So let's see what this test is all about. So suppose again we have a series A sub n and a series B of n. Again, this one, and these are series, of course, with positive terms. All the series that we're testing in this section must have positive terms for these tests to apply. With series A of n being the series that is being tested, and the other series is, again, a series that we are familiar with. We know whether it converges or diverges and when it exhibits that behavior. Okay, so this is the one we pick, and it's familiar to us. So if we take the limit of the ratio of those two series, the series that we're testing and this divided by the series we picked, as n goes to infinity, if we end up with a constant term where c is a finite number and c is greater than 0, then either both series converge or both diverge. Okay, this is very important. It's important because this series B of n, it should be a series that we know how it's going to behave. Because if it's diverging, the series that we're testing is going to diverge too, using the limit comparison test. If it's converging, the series we're testing also converges. So this one that we pick, we must be very familiar with how it behaves. Just remember that. And we can apply the limit comparison test when the limit of the ratio of those two series ends up being a real value, a finite number that is greater than 0, some positive value. Then we can use this notion here. And so this is, I made a note of it here. Maybe I should put because this, what you pick as this series to compare to is very important, so I should highlight it as well. So once again, series B of n is an appropriate series selected by you. This should be a series such that we already know whether it converges or not. Okay. All right, so let's look at an example of this kind. So here we want to determine whether the series is convergent or divergent. Notice they don't tell us what kind of test we should use. But using the limit comparison test, well, before that, let me just, in anticipation of that, I'm going to say that let's take this as, so this is obviously the series we're testing. So series A sub n is 1 plus 4 to the n power divided by 1 plus 3 to the n power. And then let's pick the series that we have to be familiar with, or series B of n, as I'm just going to borrow numbers from here, 4 to the n divided by 3 to the n power. Now, those of you who are familiar with this and the discussion we had in 8.2, if you remember that, we can rewrite this as 4/3 to nth power, but that's exactly a geometric series, and geometric series where the the r, absolute value of r is greater than 1, right? R would be 4/3. 4/3 is greater than 1. And what happens when the common ratio is greater than 1 for a geometric series? Does it diverge or converge? If you remember that discussion from the previous section, it will diverge. For the geometric series to converge, this ratio, 4/3, must be less than 1. Okay, so I just gave you a heads up on what direction we're headed. So that's where we're headed. To compare the limit of a ratio of this with something that is going to be a geometric series eventually. Okay, so let's take the limit, but for us to conclude that when we take the limit of the ratio of this divided by that, we should end up with a value that is greater than 0, right? So we still have to check this condition. So this is pretty, where c is a finite number and c is greater than 0. We need to establish that, and we have not done that yet. So let's do that. So we have limit as n goes to infinity of an over bn. And so we have 1 plus 4 to the n power divided by 1 plus 3 to the n power divided by that. 4 to the n power divided by 3 to the n power. And I should remember to put my limit. So I should put limit as n goes to infinity. So we're taking the limit of that ratio. So again, as limit of that ratio as n goes to infinity. So what do we have? Let's write this down. 1 plus 4 to the n power divided by 1 plus 3 to the n multiplied by, flip this, we get 3 to the n power over 4 to the n power, right? So notice that we have 1 plus 3 to the n power, 3 to the n power, 4 to the n power, and 1 plus 4 to the n power. So let's put these together. We can do that. So limit of this expression as n goes to infinity, 1 plus 4 to the n power divided by 4 to the n power. I'm just putting the terms so that they're together. So 3 and then 3 to the n power divided by 1 plus 3 to the n power. So I'm just rewriting it like that. And I have a purpose for that. So now, as we take the limit, so let's again rewrite this so it's easier to apply this limit. In this case, if we divide, let's divide everything. In this case, let's divide the two terms in the numerator by this. So we can write limit. I'm just doing this so it's easier to apply the limit. That's all. And so I'm just going to, so 1 divided by this, and then plus 4 to the n divided by 4 to the n, we get 1, right? So that's that. And then, so that's, I rewrote this as that. Now it's easier to apply the limit. And this one will have to do the same thing. So if this was 1 over 1, 3 plus 3 to the n, so we can write this as, we can divide every term by 3 to the n. So in here, let's divide every term by 3 to the n power. What do we get? We get 1 in the numerator. We get 1 divided by 3 to the n in here, plus, of course, 1. 3 to the n divided by 3 to the n would be 1. Okay. All right. Now we can apply this limit very easily. So if n goes to infinity, this term becomes 0. So we'll get So we'll get 0 plus 1 times 1 over, so this will be 0, 1 over 1, so we get 1. So this will be equal to 1, which is, of course, looking back at this condition for the limit comparison test, we found the limit is 1 in our case, and where c must be a finite number and c greater than 0. Then either, once this condition is satisfied, then we can say either both series converge or both diverge. So, of course, we've satisfied that condition. That quantity is greater than 0, and therefore, and so according to the limit comparison test, then either both series, we're talking about these two series, diverge or converge. Of course, this is what we're testing. This is the one we know the behavior of. So note that this series that we picked, and I'll just say from 1 to infinity, is equal to 4 to the n divided by 3 to the n. This is equal to 4 over 3 to the n power, right? So this is just a geometric series. Note that this is a geometric series with absolute value of r equals absolute value of 4/3, which is greater than 1. And when this happens, the geometric series is divergent. So thus, this one is, which is what we picked, is divergent I should say, and by the limit comparison test, this one that we were testing is also divergent. Okay. Okay, so this is an application of the limit comparison test. Remember that when we pick our series that we know how it behaves, that is familiar to us, and we calculate when we calculate the limit of that ratio, we must get a finite number that is greater than 0. That's when we can apply the limit comparison test. So up to this point, we're checking to see if we can apply the limit comparison test, and yes, we can, and then we applied it. Okay. Let's do another example. This one. So once again, let's apply the limit comparison test. And so for sure, given that the series that we're testing is this, right? It's 1 over 2n plus 3, and the series that we pick, let's pick 1 over n. That's easier. That's just so, and 1 over n. Okay, so let's establish that. Now we're going to take the limit of the ratio of this series divided by that series, right, to see whether we can apply the limit comparison test. So limit as limit of an divided by this series as n goes to infinity is equal to limit as n goes to infinity of 1 divided by 2n plus 3 divided by 1 over n, and then this we can simplify to n over 2n plus 3, and then so let's divide everything by n, which is the highest power of n in the denominator. And so we have limit as n goes to infinity of n divided by n divided by 2n divided by n plus 3 divided by n. So what do we get? We get 1 over 2 plus 3 over n, right? So applying the limit, we have 1/2, right? We have 1/2. This is, of course, greater than 0. Thus, applying the comparison test, then if this series that we picked converges, so does this one. If this one diverges, so is this one. Okay? So if we do that, so this then, and note that this series is a p series with p equal 1, right? Is a p series with p equals 1, and thus diverges. Okay, so the series we picked diverges, therefore the series we're testing will diverges too. So thus comparison test this series, and it is diverges 2. Okay. So in the next section 8.4, we will look at series that have a mix of positive and negative terms. In this section, just a quick reminder, these are all series that we tested that have just positive terms. I hope this was worth your time, and thank you for watching the video until the end. For now, have a nice day, and I'll see you again next time.